Welcome to the third webinar in the 2025 Earth Science Week webinar series celebrating the theme Energy Resources for Our Future. Today's speakers will be presenting on a variety of energy resources. One goal of our 2025 Earth Science Week theme is to highlight a range of energy resources from how they are located and extracted to how they differ in their uses and their environmental impacts. Annually, we at the American Geosciences Institute create educational resources to help formal and informal educators that bring Earth Science Week topics into their classrooms or outreach events. One such resource is the Earth Science Week calendar. This contains 12 activities and Earth observation data sets to continue to discuss energy with students and the general public all year round. The first activity, which was sponsored by the American Association of Petroleum Geologists, has students analyze data on multiple energy resources in the U.S. It also provides a curated set of links for students to learn more about different energy resources, reservoirs, and deposits, many of which will be highlighted in this webinar. This was chosen as the first activity in the calendar to be able to introduce a variety of energy resources and mineral deposits. The activities that follow then look at natural energy resources from electric charge in soil, to geothermal features, to using solar power, and the minerals used in sustainable energy sources like geothermal, wind, and uranium. The activities then progress into the use of energy resources, where students look at maps to determine what energy resources their community uses, to what their specific school uses, and how exploration for energy resources occurs, including looking for rock layers that can be used for carbon sequestration, and also considering their environmental impacts. So as you can see, the progression of activities within this calendar build on each other to look at a number of factors that go into considering what types of energy resources communities use. So the presentations you'll see today will cover a range of energy resources, starting with Helga Helderson, who has 47 years experience in the energy sector and who is currently the alumni in residence at the University of Texas at Austin, who will speak about exploration for hydrocarbons.
Well, thank you, Lindsay, for that kind introduction. Let's talk about exploration, one of the coolest things you can do. So let's get the big picture first. We're all on deck of the blue marble, as they call it. You see it there? Rotating around Earth axis at 850 miles per hour. That's what you're doing right now. But that's not all. You're racing around the sun, a free trip once a year, and the speed is 67,000 miles per hour. You know how quick that is? That's 40 times the speed of a bullet, and you're doing it right now. I mean, is that awesome? If you send up astronauts, regardless of political party, they get what's called the overview effect, a strong sense of responsibility for all on the blue marble. So for a moment, let's all be astronauts. Let's zoom now in on the blue marble. I call it Spaceship Earth. We're 8.2 billion people in 200 nations. More than 2 billion people of the 8.2 is without access to clean cooking. And we get lots of new customers for energy every single day. We get 200,000. I'm in Austin. Austin is about 1 million. So we get a new Austin every 5 days who wants energy. Last year, we used 620 exajoules of primary energy. More than 80% of it came from fossil fuels. We used 103 million barrels a day of oil, 400 BCF of gas, 400 million tons of LNG, 20 million tons per day of coal. And when we burnt that, we sent up almost 40 gigatons of CO2. That triggered climate change. The temperature is going up. Local and ambient pollution. By the way, Landslet says that local and ambient pollution prematurely kills 9 million people per year. And then we have climate change effects on top of that again. So what are we trying to do? We have the Paris Agreement, which is difficult, but keep temperature increase below 2 degrees. And while we're doing that, the world is heading for doubling of the world economy, from 100 trillion in 25 to 200 trillion in 2050. Tough to do those two at the same time. And we're in 200 nations, as we talked about, with very different starting points. and very different trajectories to 2050. But longer term, we will probably build down the high emission energy sources as we ramp up the lower emission energy sources, but we need to synchronize the two, otherwise we get a series of energy crises. So this is the use of primary energy since 1965 to today. And as we talked about, more than 80% comes from oil, coal, and gas. Let's focus on oil. Where's the oil production coming from? And here you see the different colors with, on the bottom, onshore conventional crude, big share, shallow water in lighter blue, then deep water, and then NGLs, and then tight oil on top there in red. Look how it's growing. That's the Permian and Eagle Ford and all that, and extra heavy bitumen from mostly Canada on top, adding up to about 98 million barrels a day. If you ask how much oil do we need the next 25 years, here is Rystad Energy's 3 scenarios. A fast one on the bottom in green, that's oil demand versus time in green. Then the brown in the middle, the base case, and then the slow transition on top in the red. And many believe in the red, very few believe in the green, but in the mean case, we need 629 billion barrels of oil, right? Between now and 2050. And that's an awful lot of oil to come up with in terms of new supply. We need to have a decent oil price to do it. And when I think back on my career, you know, what has happened to oil price? Always boom and bust. I think I've been through 6 bust periods where it goes really low. And we never know if we're on the way up or on the way down. So when people ask me, today it's around 65, what's going to happen with oil price the next 25 years? Nobody knows, of course. And we don't even know, today is October 9, if we're on the way up or on the way down. Some do believe in a new upcycle because we have maybe been underinvesting, but some people say that no, we have not been underinvesting, so we don't know. If you run a company, you need a portfolio that's fit at a certain price, right? You don't bet the house. And should that be fit at 50 or fit at 40? I don't know, but every company is working on that. So let's look at conventional exploration spending from 2010 to 2024, and then an estimate for this year. In 13, we used $117 billion to exploration, and in 25, it looks like we're landing on about 50 billion, less than half of what we did in 13. Why is that? It has fallen because many investors have felt that new discoveries could end up being stranded because of the ongoing electrification of vehicles, and also the possible slump in both oil demand and crude prices. Nobody knows, right? But that's one theory for why this has happened. Another one is that we don't need so many wells because we keep finding more because we're smarter with technology. So where do we drill? Here you see in 24, the light blue is ultra deep water. Look how much went to ultra deep water and who drilled there as well, the company names. Then you have the deep water in darker blue. Then you have the shelf in brown and land in greenish on the bottom. So here you see where the exploration spending is going. And this is the classical situation when you come out of school and they send you offshore Brazil, Norway, or West Africa, any oil here, right? You bought the concession and you have the rocks below, but this is kind of what you're faced with. And if you are working onshore in South Texas, this is what it looks like, right? And you did your homework, did everything, and then you put the rig there, and you wonder, how did they decide to put the rig just here? When I talk often to people who don't know anything about geophysics or exploration, I compare what we're doing to an ultrasound. When people go and look at, what's going on. Is it the boy? Is it the girl? Is everything fine? That's exactly. We send sound waves down to get the picture and image of the subsurface. Onshore, of course, we have a truck banging the ground, creating sound waves, and then we lay out cables to receive the signals. And offshore, we have explosives that creates the waves for us. They go down, hit the formation, come back up, and are recorded in a cable that we drag behind the boat. And in both cases, we end up with a seismic cross-section, right, that tells you what it looks like down there. So these are the two babies that we have to work with in exploration. The funny thing is that different sets of eyes and companies often see different things. I have seen companies go in with 50% in a concession. They love it, but then all of a sudden they don't love it because they have a new interpretation. So they leave the block, right? And almost give away half the 50% they had because of the view they have on what they're seeing. Company one can say, oh, it's a gas here. This is a big oil field, this is fantastic. Just condensate, it's not going to be that profitable. Oil, but too small. And I don't really see anything. If you drill a well here, it's going to be a dry well. So the diversity of opinions is just have amazed me, in my career, right? If you look at what we find, this is showing kind of for ranges of years from 60 to 69 to 20 to 24, how many billions of oil equivalents, so you add up oil and gas in BOEs, are we finding? And now you see we're down to 9 billion BOE, and look at that compared to what we found in the 60s. So we have all kinds of numbers up here. Much better exploration because we hadn't found the big frontiers in the 60s. More difficult to find things now. And also the size of what we find is smaller. In the 70s, there were 150 million BOE per discovery. Since 2010, if you take the average of field sizes we have found since then, we're down to 14 million BOE. Some exceptions like Guyana, we found billions of barrels, and Mozambique when it comes to gas. So exploration and field development technology keeps evolving. We had 3D seismic after having 2D seismic, and then the processing is evolving. So let's call it exploration 2.0, 3.0, 4.0. And some of the things that are happening is, of course, better sources, better data, better seismic processing, more advanced digital technologies, more enhanced acquisition and processing and imaging. And here comes artificial intelligence and machine learning. Here we're looking for pattern recognition, so we can see the signal kind of when we found oil and when we don't found oil, to put it that way. And then when we chew through loads of seismic, we kind of recognize a pattern that looks promising, and then we drill there. And many companies in papers that they have published have reported already measurable successes with AI and machine learning in exploration, in phases modeling, and also to predict properties like porosity, permeability, faults, and what have you. So when the exploration manager comes to the top of the company asking for money to drill a well, in my career, I'm always more impressed with the one who says, it should be oil here. We've done all the homework. There's nothing more we can do. We believe in it. We're confident it should be oil here. Rather than one that comes in and says, it could be oil here. It could be oil here is more like multiplying 4 risks with each other and getting something that's higher than 20%, and then it could be oil here. I like the blue one much better. Drill here. Then we bring in a rig offshore. In shallow water, we call them jack-up rigs. They are now up to rig rates of 110 to 200, depending on how big and impressive they are in terms of what they can do. And for the newest drill ships and drilling rig, the semi-submersibles, as we call them, they are now back at maybe $400,000 to $650,000 per day. Pretty expensive taxi to have out there. So you want very little what we call NPT, non-productive time. You want to keep going and not waiting for anything. So you drill the first well, you have a discovery, you drill the next one, and a few times in my career, we have champagne in the fridge, and here we go. Cheers. Very important. You drill through the reservoir, you get cores and logs, you look at them, you understand the depositional environment. And then people like me in my career, beginning of my career, I was going to simulate it to look at production of gas, oil, and water the next 30 years. very important to go to an outcrop, in this case a turbidite, to see what they look like, right? So that you have a realistic reservoir model. And then you develop the field, and then it produces for 34 years. And we hope that your predictions are pretty good, so you install the right capacities. In the Permian, of course, it's very different. The Permian, you're not doing a lot of exploration. You kind of know the extent of this massive Permian formations. They have different names, but I won't go into it. Here it's more exploring different ways of drilling, of completing, of fracking, and what have you. But the length of Permian wells now are up to 2.5 miles, right, which is enormous. And after having drilled 100 of them, the surface looks like this. Unbelievable. I did the beginning of my career on the Norwegian continental shelf after getting my master's. And the Norwegian continental shelf have turned into a fantastic offshore laboratory. I have a long list of unbelievable things that was done here kind of first. I would say because of a lot of good policies that were introduced. When it comes to the money coming from the Norwegian continental shelf, the politicians, I felt, have been very smart. They put it not to the politicians for annual budgets, they put it into what's called the Norway Sovereign Wealth Fund. That is now the biggest sovereign wealth fund in the world. Asset under management is $2 trillion. They own 1.5% of all listed companies. And government do get some money for the annual budget, but only the interest, about 3% of it. But 3% of 2 trillion is a lot of money. We are 5.6 million Norwegians, and if you divide 2 trillion by 5.6 million, you see that each of us have $350,000 in the bank, which is pretty good. I want to show you one field, kind of, to show field development 2.0. It's called the Johan Sverdrup field. It produces more than 700,000 barrels a day, almost 3 billion BOE of reserves. The break-even oil price is less than $15 per BOE, and the operating cost is less than $2 per BOE. And the carbon intensity is less than 1 kilo CO2 per BOE. I have here that the world average is 15. I think it's 16, 17, 18-ish. So this is an unheard of low carbon intensity. And how is that possible? Because we have an electricity cable from shore, so we don't need to run gas generators to get power on all these 5 platforms. The recovery factor ambition is 70% because of loads of plans for IOR and EOR and infill drilling. Look at the one last, the PRM, Permanent Reservoir Monitoring. This is a field that looks like this in terms of the area. The reservoir is about 1,900 meters deep, water depth 110 meters, and we're talking about 200 square kilometers of reservoir area. What they did was to install 6,500 permanent sensors on the sea bottom over the field. Then they connected them with 380 kilometers of fiber optic cables. So now they can kind of run ultrasound of the Johan Sverdrup field every day if they want. So they can see unswept areas and where to put the next infill well. So here is Ed Robeck, the Director of Education and Outreach at AGI, and me, sitting here in Austin at the 40 acres where we have UT at 11,000 BC. And Ed says to me, I wish we could go to the moon. I said, Ed, are you crazy? We can go to the moon. All we have is flint arrowheads, which was true. That was the most high-tech stuff anywhere in the world at that time. But then, as we all know, we did, because the visionary JFK and 400,000 people working hard for 10 years, not quite 10, $280 billion. That was more kind of 2% of US GDP in that period. And lots of important things that I list here that I won't bore you with reading, but this is pretty impressive. So I'm saying, if we could go from this to this, and my daughter used to live in New York, if New York could go from this in 1856 to this New York, let's see it one more time. It is unbelievable, isn't it, how New York has changed? Then we can certainly go from this energy mix to another energy mix. given enough time, good students, good professors, enough funding, good leaders, good policies, sufficient investment, international cooperation, R&D, and innovation, both radical and incremental. And I think, therefore, it's never been a more exciting time to be in energy. We have a generational challenge to all the way to 2100, to get energy to, I think in 2050, we're going to be 9.8 billion people. But in the meantime, we have to get energy to all, including those 2 billion with almost no energy at all. So with that, thank you very much for your attention.
Thank you, Helga, for sharing your insights on hydrocarbon exploration and your positive outlook on the potential shifts in the energy sector. Next up, we have Ashley Dowds, a research geologist at the Indiana Geological and Water Survey at Indiana University, and who was also past president of the Energy Minerals Division of the American Association of Petroleum Geologists, who will speak about the role of geologists in the exploration for lithium and uranium and their roles in the energy sector.
Hi, and thank you for attending my presentation today. My name is Ashley Dowds. I'm the past president of the Energy Minerals Division of AAPG and a research geologist at the Indiana Geological and Water Survey at Indiana University, Bloomington. Today I'll be talking to you about lithium and uranium, resources for a lower carbon economy, and the importance of geology. So, petroleum geologists study various aspects of the subsurface and varied types of geologic deposits. The Energy Minerals Division of the American Association of Petroleum Geologists, or AAPG, is comprised of members who are interested in studying the formation and distribution of many different economic deposits. Lithium and uranium are commodities within the Critical Minerals and Uranium Committee. You can see that we have various other committees studying aspects of energy minerals, and if you would like more information, please check out our website and reach out. So, the U.S. Department of Energy has released a short-term, meaning 5-year, and a medium-term, over a 10-year period, outlook for raw materials that are critical to our energy infrastructure. Lithium and uranium exist in the same near-critical quadrant for the importance to energy on the y-axis and supply risk on the x-axis in the short-term outlook. Whereas in the medium-term outlook, lithium jumps to the critical quadrant. Over the next few slides, I'll show you some of the reasons why lithium and uranium are critical to our energy infrastructure, the geologic settings where we find these elements, and why understanding the geology can lead to new sources and extraction methods. So, as we saw in the last slide, lithium and uranium are critical elements for incorporating lower carbon energy technologies into the energy mix. Traditionally, these elements have been mined at the surface or in the near surface, as shown on the image of a pegmatite mine that was where lithium was extracted, and then the graphic for a breccia pipe uranium mine. These elements need to be mined for the lower carbon energy technologies. But the challenge now is to find additional sources using geologic methods, characterizing that resource, and then using that knowledge to develop extraction methods that may reduce the environmental impact of mining these deposits. So let's start with the numbers for electricity generation. This graphic from the Visual Capitalist shows that in the US, fossil fuels made up roughly 60% of the power generation in 2024. Renewables, that includes solar, wind, and geothermal, came in at 23.3%, and nuclear was 17.9%. So, if we look at the growth in these segments over time, electricity generation from renewables in the US, measured in gigawatts, has increased roughly 50% from the time period of 2018 until 2024, according to the U.S. Energy Information Administration. And if you look at a breakdown of those renewables by source, wind and solar have had the most dramatic increase over that time period. And then in the forecasted region, solar is forecasted to increase at a rapid pace into the future. With this increase in electricity generated by renewables, there's been an associated rise in the battery storage capacity additions at the global scale to store energy generated during peak generation times and releasing it to the grid when needed. So you can see the importance of having batteries to assist with the transition to more renewable energy on the grid, as well as for electric cars. Pay attention to this spot right here on the graph, which is 2021. Notice how the graph grows exponentially after 2021 regarding the rate of battery storage capacity additions at a global scale. So this graphic shows the rise in lithium consumption globally from 2010 to 2021. Over that time period, there was a 283% increase in consumption of lithium at the global scale. Remember how the last graph stopped at 2021 and the rise in battery capacity continued to be exponential after that date? This graphic stops at 2021. So just imagine what an updated figure would reflect. Exploring for new sources of lithium and innovative mining techniques are an underlying driver for lower carbon energy. A majority of the lithium supply for batteries is in the form of lithium carbonate. The preferred chemistry for lithium iron phosphate batteries. However, lithium hydroxide is the preferred form for higher energy density chemistries like those using nickel, manganese, and cobalt. Lithium carbonate can be converted to lithium hydroxide, but that does include an additional cost to the generation and extraction of lithium. Notice the percentages of lithium sources from the USGS based on 2013 statistics and the various geologic environments or minerals they occur in. The blue highlighted sources are from fluids and the reds are from rocks. They constitute uniquely different geologic settings and therefore require the resource to be characterized to understand how best to extract it. Understanding the geochemistry, which is the combined geological and chemical basics that the forms of elements like lithium take, and the geologic conditions they are found in, allows us to understand how the lithium is incorporated into the chemical formula, and then how easy or difficult it may be to extract that element from the mineral form. And that information is critical for developing innovative technologies for extraction. Next, let's look at the different types of lithium geological environments. Subsurface salty waters, also known as brines, can contain sources of lithium and make up to 58% of the supply, again by 2013 statistics. The methods to concentrate the lithium salts can be in a natural environment known as a salar or in a man-made evaporation pond or salt pan, as seen over here on the left. The salars form enclosed basins, meaning the waters are restricted to that basin. They are tectonically active and are in arid regions. The salt pans shown in the bottom left have different colors because of the chemistries, either from various minerals or organisms that are in the ponds. Another traditional source of lithium are spodumene pegmatites. Spodumene is a lithium ore mineral found in pegmatites. In North Carolina, there's a zone called the Kings Mountain Shear Zone at the boundary of the Kings Mountain Belt and the Inner Piedmont Belt, where pegmatite dikes can be found and have been mined in the past. Pegmatites are a type of mineral formation with large grain crystals that formed over a long enough period of time to create and generate these big crystals. In this area, the formation of pegmatite dikes is related to the presence of faults, as seen on this map over here. So these gray traces represent the faults, the mapped faults, and then the reddish-brown lines here represent where the pegmatite dikes are. Another depositional environment for lithium is in altered ancient volcanic deposits. So one that's gained a lot of attention recently is the McDermott caldera. A caldera is a collapsed feature over a dormant volcano's magma chamber. And this McDermott caldera originated from a Yellowstone complex supervolcano about 16 million years ago. Thacker Pass is an area within the caldera region that shows that has these altered volcanic ashes that have turned into a lithium-rich clay. There are also ancient soils that developed within sedimentary rock sequences that can have anomalously high lithium. So underclays, the clays that we see closely associated with coals, can have high lithium content, and these are essentially paleosols, which means that they are ancient soils. Here's an example of some data from Illinois Basin underclays or paleosols associated with Illinois Basin coals in Indiana. So over here is the stratigraphic column of the Pennsylvania coal interval. The red horizontal lines represent paleosols associated with those coals, and they were analyzed for lithium content. And you can see that some of these coals can show contents over 500 parts per million. Other news sources are also subsurface waters of oil and gas reservoirs. Waters recovered after well completion are called flowback waters and can contain a couple hundred milligrams of lithium, milligrams per liter of lithium, and vary across formations such as the Marcellus Shale that we see here. And it may be related to the clay content of the shale as well. We also see the Smackover Formation along the U.S. Gulf Coast is known for high lithium content of the subsurface fluids and has actually been in production for years now. So when looking at the various sources of lithium, it's important to understand the environmental impact of the ways the lithium is extracted from the source. Conventional methods of lithium extraction from brines can impact land use, water use, and depending on the energy source, can generate emissions. Newer extraction methods, such as the various forms of direct lithium extraction, or DLE, can call on various chemical processes to extract lithium and potentially reduce water use, land use, and emissions. But with each extraction method, evaluating the trade-offs is important. So now let's look at nuclear energy. This is a source of low-carbon energy that has gained momentum lately as the need for additional energy sources became apparent and new technologies like small modular reactors were developed which allow for quicker deployments than the standard power plant that can take years to acquire the necessary permits. So many nuclear power plants need to sign multi-year supply agreements. However, a recent report from the Energy Information Administration showed that the contracted supply, here in dark gray, via these agreements does not equal the required supply, which is this combined amount up here, indicating that there is a supply gap in uranium that grows over time. Therefore, although uranium employment had been decreasing over several years, we see now that there's beginning to be an uptick in employment in the uranium production industry, including in these green bars is exploration. So more work is being done to find new sources of uranium within the U.S. The mines that are currently known are mapped here and are mostly present in the U.S. West as well as Texas. So uranium can be found in several different geologic settings. The most common settings in the U.S. are in breccia deposits, like the depiction on the earlier USGS diagram, and the roll front type deposit, where uranium is deposited in porous and permeable sandstones after a chemical reaction of oxidized fluids move through the sandstones and create a redox front. Understanding these different geochemical environments allows for geologists to explore in more geologic settings, looking for deposits that can be extracted to reduce the supply gap for the lower carbon energy future. So to sum up, exploration for lithium and uranium deposits is increasing as they are necessary components of lower carbon electricity generation. Geologists are critical for understanding these resources, finding them, and characterizing the deposits in order to develop new extraction technologies. My references are included here. Thank you.
Next up, we have Stephen Tedesco, President and CEO of Running Foxes Petroleum, who will speak about helium reserves and their potential use.
Hello, I'm Dr. Susan Nash, and I'm here today with Dr. Stephen Tedesco, who will talk to us today about helium. So, Steve, first of all, tell us a little bit about yourself.
Sure. I live in Centennial, Colorado. I graduated with a PhD from the Colorado School of Mines. I grew up in the Boston area where I went to Northeastern University for my Bachelor's of Science, then went to Southern Illinois University in Carbondale to get my master's. I've been in the business probably about 46 years. I've been operating my own company for at least 44 of those years, and I've been very active in the West and mid-continent part of the country, as well as back east in Kentucky. I'm a geologist by training. I have also a petroleum engineering background. I operate presently about 400 or 500 wells in 4 different states, and I love geology. I didn't start in geology in undergrad. I started in 4 other majors before I took a course by accident in geology, and then the rest is history. I always thought that geology was more about the weather because they called it earth science or other names that weren't specifically for geology in high school. So I got my start really in college, but I think it's really good when people start it early on and in high school get interested, maybe even middle school if they like rocks and fossils. And I started out wanting to be a paleontologist, but then I found that I really enjoy finding things in the ground and oil and gas and helium, various base metals, lithium, uh, variety of things. It's all fun to do. It requires a lot of thinking, and it's like being a detective in a police force, except you don't have to arrest anybody. You produce things for a profit.
I love it. It's just so interesting.
Yes, it
Well,
is.
tell us a little about helium then.
Okay, well, helium has become a unique opportunity in the oil and gas industry. Helium is typically found with natural gas, and then it's separated at some point in the processing of natural gas before it's sold to heat your house or run power plants that generate electricity. So it's become even more important because AI needs a lot of helium, but there's a lot of things that need a lot of helium, and without helium, we would not have our modern society. Cell phones wouldn't work. We wouldn't be able to weld steel. A lot of our medical equipment would not work to the level that it does right now. Helium is basically used in a lot of different things, and this screen shows that. It's quietly out there, and if we go to fusion or fission, we will need 20, 30, 40, maybe 100 times more helium because it access the atmosphere for the fusion reactions to work. So helium is very critical. The United States, for the history of helium, up until the past 20 years, was producing almost 100%. Now, a few other countries are producing helium, but it's still very much limited to the US and Canada. The Canadians have started producing significant amounts of helium in the past 5 years. So the search for helium is ongoing, and it's really fun to do, and because you have to do geology to find it, but there's a lot of fun things when you do the geology. So if we had no helium, no MRIs, no computers, the computer down at the bottom right is what the computer you would have without helium. Your cell phones wouldn't work. MRIs would not work. We'd not be able to grow our our, our chips to the perfection they are for computers, and we would not be able to weld efficiently without helium. The best welds in the world for steel are with helium.
Well, I'm sure everybody's clamoring to know, well, how about party balloons?
Well, party balloons is a minor part, but that's what everybody
What?
remembers. Helium, helium has gotten very expensive, whereas natural gas sells for around $3 uh, for a unit, which we call MCF. Helium sells for about $400 to $500 a unit or MCF. So you can see how it's very expensive, and a lot of countries are trying to find it. China, for example, doesn't have much helium. Russia does, but Russia's being banned. So it's one rare earth that we have over the Chinese is helium, and they desperately need it. And right now they're getting it from Russia. But for the rest of the world, they buy a lot of American helium, and there's some helium in some other places like the Middle East that provide it. So it is becoming more and more in high demand, and it will only grow. Now, helium, all it is the most inert element. It doesn't react with anything unless under extreme conditions, but it is the second most common element in the universe, or so we believe, after hydrogen. It's the second smallest. It is basically it smiles at you, will not react with hydrogen, will not react with oxygen, just doesn't do anything. It's chemically inert and non-reactive, and that's why it's so critical, is because it's perfect to grow crystals inside a helium atmosphere.
That's really fascinating.
Yes, it is. I mean, it, it up until about 20 years ago, maybe even 10 years ago, no one was really looking for new sources of helium. It was basically coming from three areas in the US and some smaller accumulations, but essentially it's really taken off because the price in the space of 15 years has gone from around 30 to $35 to over $400. And it can be very economic for the companies that find it. And this is just a chart showing the reserves and productions. You see they go up and down. Helium was first discovered by the British during World War One. Like the Germans, were flying Zeppelins or hot air balloons that used hydrogen, and hydrogen is highly flammable. And subsequently, the British found out that 10% helium in the gas mix, that when bullets hit the uh, balloons, they would not blow up. The Germans had no source of helium, but the British did. As a matter of fact, the British found the first source of helium in Ontario, Canada. By the time they finished the extraction facility, the gas wells that they were going to extract it from ran out, but then they moved to Alberta and Saskatchewan, where they started producing helium, and that was the first start. In the 1920s, the US found more significant helium in Kansas and down in Texas, and that is the Texas Panhandle and Hugoton Field, which have provided a major source of helium for the world, let alone the U.S. And then, in about 20 years ago, Exxon found the most recent large field in Wyoming, in the southwest corner. So right now, we're producing between 40 and 50% of the helium for the world, and we continue to find more in this country, which will just keep us in business for a long time. Now, where is helium? Well, like I said, it's in the US and Canada. These gray areas are basins, geologic basins. The helium is found with old rocks, generally older than 400 million years. Occasionally, it's found with younger rocks, but those are directly sitting on top of what we call Precambrian granite or basement. Now, this map is color coded. The higher the color represents the more rich the gas is with helium. So the turquoise color is areas that are low in helium and not economic at present time. They may someday become economic. The reds are obviously the hottest areas, and you can see that they're in Kansas, Utah, New Mexico, Arizona, up into Canada. And actually, this map is about 5 years out of date, so it's even hotter up. The numbers are good up there. They're just drilled more wells. And then in the east part of the country, not much has been done because a lot of the gas analysis that have been submitted for public use are very old, and we question the helium values. We know now that some of them should be higher than they represented years ago when they were taken. But this is just to give you a general idea. Like the west coast of the US does not have any real helium in it because the rocks are too young. And so what happens is the helium comes up from the mantle and the lower crust, several miles, and it migrates up into our shallow rock section where we find oil and gas and minerals. We find groundwater. We find all sorts of nice things and great geology to look at for oil and gas. It's a lot of fun. But then the helium migrates into shallow accumulations of natural gas and accumulates with the natural gas. Helium also accumulates with large deposits of carbon dioxide and nitrogen, as well as we're finding it now with hydrogen accumulations. The hydrogen accumulations, unfortunately, are very low pressure, and so far they're not economic. But the helium in those deposits is very high in concentration too. Now, this is the Big Piney Labarge field. This is the Exxon field. It's a huge area that's being produced. Another part of the field is being opened up to provide helium for the world. It's backed by a local U.S. company here in Denver and by JAPEX, which is out of Japan. But
Now,
it's
where
very
is Big Piney?
You see this area up here.
Okay, which state?
Oh, I'm sorry, Wyoming.
Okay, perfect.
And then they're opening up this area down here. So it's really, and it's very complex geology. It's actually near some volcanic activity, which is providing some of the helium. This is one of the bigger fields in another part of the world, the Middle East. We all know this area from all the problems that go on there. But Qatar became a major gas player 40, 50 years ago with the discovery of the Pars field, which is split between Iran and Qatar. And this is the largest natural gas field in the world, several TCF of gas, but it all has a low percentage of helium. But because of the size of the gas field, it's providing about 20% of the world's helium. And it's a very interesting geologic area. This is in Algeria, same thing. This field actually was discovered a while ago. This field is still producing after 30, 40, maybe 50 years. But it's a very, helium's very unique, but they're producing it here another 20%. And then here in the US, you get to Texas Panhandle. This covers 3 states, or three states, and it's just southeast of Colorado, into Kansas, down in Oklahoma and Texas. And this is where the majority of helium has been produced over the past 100 years actually now. So essentially, this is a very large field. It's still producing, but it's near the end of its life. But they are storing helium from other areas into it. So this is a lot of great geology that's going on. Now, this is an area that I've worked. I just made a new helium discovery out here. The picture of the facility there is next to Harley Dome, and Harley Dome was one of the first helium discoveries. It's been producing now for about 20 years, even though it was discovered in the 1930s. But this area is very shallow, and so for small operators like me, this is great to work around it. But it's great views of the Rockies. The Wasatch Plateau is behind there, and it's in a desert, so a perfect place to find resources. This is in Kansas. This is one of our smaller fields. And then the bottom map shows you all the gas fields that are in Kansas and oil fields. That red area is the Hugoton field. So you can see that it's very large. But we find now a lot of our helium in these very small fields. And it's very economic when you find it. And it's fun doing the geology. This is in southern Colorado. This is a brand new play, and I like this play because it has great graphics. But this gives you an idea of the type of geology. These little uh, uh, rectangles here, those are wells that were drilled, and then that way they could map out the geology. And here's the Precambrian basement, but this is generating helium and then putting it into this structure and accumulating there. And this gas is with CO2 and nitrogen and very high helium contents, but very low flow rates. So it produces some helium, but not the amounts that we would need to be significant. And this is more geology that people put together, and you can see how exciting this would be trying to map all of this stuff. It's just another example of the same area. I just like their
Just
graphic.
so fascinating. Yes, it's
Yeah,
so interesting.
right. Now, the Entrada is where the helium accumulates, not in the Morrison. That doesn't have a
Hmm.
place for the helium to sit in pores. And pores are those openings where we can hold fluid like groundwater that we drink, or oil and gas, or salt water. And this is very uniform across a great area, but this is also which they get their drinking water from down there. So when they produce the helium, they have to figure out what they're going to do with the groundwater. And a lot of the ranchers like it to come out of the ground because it helps feed their cattle.
And it gives the cattle really high voices.
Yeah. But you can see here's a more detail of one of the previous ones. And, some of this is very artistic license, but it gives you a sense of the geology and how things change across distances and that sort of thing. These names up here are their prospect names. The Model Dome is another one like Harley Dome that was discovered in the 20s. It's produced helium off and on in three stages of exploration and extraction since then. And it's making a little bit helium now. And then there's areas across the world like Tanzania, and this is a seismic line, and you can see all these lines represent the top of geologic units, and you can see how complex this is. This is near a very volcanic region called the East Africa Rift System, and this is very active. There's lots of helium coming out, but so far, it's been not been able to be proven economic, and it's in a place that's very distant from facilities and contractors to work. So it makes it tough, but great seismic cross sections and that sort of thing. And then this is a map of looking down on it. So like that line is right here, and this is a big fault area, and so on and so forth. So in summary, helium is a critical element needed for modern society. Helium is related to uranium, thorium, and lithium decay, which I didn't go over. But essentially, what we're seeing is helium is generated from these elements. The majority of helium is in US, Qatar, Algeria, Russia, but that is changing. The central part of what we call the mid-continent, or the US, Southern Rockies, Alberta, and Saskatchewan, that's where we find helium right now. And finding these reserves is difficult, which makes it even more fun when you find it. Recovering the helium from the gas stream is expensive. I didn't go over that sooner, but it's basically you have to buy equipment that's very expensive, takes a year to put into place, but it can be very worth it. So, however, provides a unique financial opportunity for many independents like myself. And this is the sort of thing that if you get into geology, you can go into, and you can have a lot of fun finding it and producing it. And I would always suggest students to go to at least take a geology course to see if they're really interested. But thanks, Susan.
I love it. Well, thank you. Thank you, Dr. Tedesco. This is wonderful and really appreciated. So if people have any questions, your information is in the first slide. So you might get
Contact me
contact.
anytime.
Great, great.
And if you're in Colorado, I'll come by and give a presentation to your kids.
I love that.
Yeah.
Thank you.
Or just on geology in general. So,
Love it. Thank you.
thank you.
So for our last presentation today, I wanted to share a little bit about AGI's Geoscience Career Explorer. This website is intended for students from middle school all the way through undergraduate, or really anyone who's interested in exploring careers about the geosciences. We try to include two categories of careers on here. One are direct geoscience related careers, while others are what we call Geoscience Plus, meaning that they require some background in the geosciences, but people may not even be really aware of that connection. And so we wanted to recognize those as being connected to the geosciences and requiring that background. But we wanted people to be able to look at careers through the lens of global issues. So we connected these careers with the United Nations Sustainable Development Goals. And if you're not familiar with those, these goals, there are 17 of them, take the world's issues and put them into 17 categories, from no poverty to quality education to industry to responsible consumption and production, and then some that are more directly related to the environment. We find that students are really interested in helping human populations and the environment, and so it makes sense for us to put the careers in the lens of these goals and what people are doing to achieve them, and specifically people in geoscience professions. So in the actual Career Explorer, you can select a United Nations Sustainable Development Goal that you're interested in working toward. And then in a more typical Career Explorer fashion, things that you like to do can also help narrow down that list. So if we start with SDG 7, which is affordable and clean energy, since our Earth Science Week theme is all about energy resources, we click on that, we see that there's already 58 careers that have been found. So that's out of the over 170 careers that are on this site. They are organized into categories. So architecture and engineering is that first category, and you can see the careers that have been identified related to SDG 7. Now, some have more direct connections, some have stronger links to SDG 7 of affordable and clean energy, as you can see, petroleum, solar, wind energy, okay? And some may not seem to have as strong connections, but when you go through and read their descriptions, you'll be able to reveal some of those connections within there. And you can see there are many different categories and looking at the different careers that fall within those categories. So if we take things that you like to do, and especially ones that align very well with SDG 7, so we can look for being creative or innovative, because as some of our speakers have talked about today, we are in need of innovations in the energy sector. And then also, let's go with solving complex problems, since that's something that's directly related to innovating. So then we now have 28 careers. As we go down, we can see those lists getting narrowed further and further. And then you're able to actually print off the results from this to get a very easy report of what careers you connect with. And so you can go through and try out different SDGs, different things you like to do, but maybe you're saying to yourself, I don't know that much about the SDGs. Well, we have a page on educator resources that'll allow you to explore more about the connections, especially with the geosciences. So there's a small description of each one of these SDGs, and then also what geoscience concepts relate to those. So we call these educator resources, but really, again, anyone who's interested in learning more about the SDGs and how they relate to geoscience can go through this and see those connections there. Another way for students to really explore what they care about and what they're interested in is through our brand new Sustainability Interactive. So this was made through funding from AAPGF, and it has real-world scenarios in it that allow students to look at a problem, and it breaks it down into the components of that problem, and they choose the ones that they are most concerned about. So they could just say, okay, this is not something that is of concern to me, and skip that just by hitting continue, or they could even go through and click all of them. And what this is going to do is it's going to give them points toward each statement, depending on what SDGs they connect to. And the output is going to be what SDGs they're most interested in. Each of these components and scenarios was based off of the SDGs. So let's go to affordable and clean energy. And we can see that it's broken down into targets and indicators, because when you say the issue is clean energy, then that is a very large issue to tackle, and that might be hard for students to really wrap their minds around. So looking at the targets and indicators give more measurable, approachable ways to tackle some of these issues. So the components of those real-world scenarios were based off of these targets and indicators, which are much more direct and measurable actions. And so when students have completed all the scenarios, they are going to get a report showing their 3 highest SDGs and the points that they got toward that. They'll also get a breakdown of their selections, and then they can explore more about the SDGs, so they can start with the Career Explorer and really know what SDGs they should be selecting when they look for careers. Another resource on our educator page is the guides that go along with the Sustainability Interactive and the Career Explorer. So just ways to use this with students or other groups. And specifically for the Sustainability Interactive, each scenario here is now broken down into the components, showing you what SDGs and specific targets line up with that and why. So if you are not sure about making those connections with the SDGs, this is really going to help you do that and really discuss with students and other users of this website, why they're interested in certain things, in what these scenarios really reveal about that. As for the Career Explorer guide, There's guidance for helping students identify interests, understanding the connections with geoscience, and why this is important. So we hope that this Career Explorer is something that you find useful to use with students or other audiences to get them interested in careers, not only in energy, but in the geosciences. Because as some of our speakers today have talked about, there is a decline in the number of students going into geoscience-related careers, especially in the energy sector, and we know that those are careers that we need to fill in the future. And again, thank you for funding from the U.S. Geological Survey and AAPGF to be able to create this Career Explorer resource. Thank you for attending today's webinar. We hope you enjoyed the presentations, and we also hope that you are able to tune into our final presentation with many speakers from the U.S. Geological Survey and others talking about Geologic Map Day and the resources that have been made for that, as well as a new national cooperative geologic map. Again, thank you for attending, and we hope to see you tomorrow.